Assalamu alaikum. I welcome all of you to the lecture series on basic concepts of chemistry. Again, today we will be discussing hybridization. Now, today we will be discussing Sp2 hybridization. Okay, what Sp2 hybridization is, and what are the energies of the orbitals, and what are the geometries of those orbitals, and how they look like in space, or just like we explained the Sp3 hybridized orbitals. Okay, so let's start from the carbon. Okay, first we explained CH4 molecule. It has all the CH bonds are Sp3 hybridized. Okay, and it was formed by like this. Okay, it is 2s and it is 2p. The 2p has 2s has one electron, and it has again one electron each, and it's when carbon was in excited state. Okay, excited state, we saw it okay earlier in the previous lecture, or lecture before, 2 lectures before this one. So it was the case of the carbon. Now in the previous case, when the carbon was excited, first, as you know, that it was in a ground state. After this is a ground state. After that, it was in a ground state. It has like this electronic configuration carbon atom has, but one of the electron moves here. Don't worry whether it is px, py, pz, because they are all similar or same energies or degenerate. Okay, suppose it moves to here. Now we assume that it went to the px, py, or pz. Px, yz, just say that they are perpendicular to each other. Okay, so it jumps here. So let's go first of all, because as I told you, mentioned earlier, that what hybridization does, hybridization explains the bonding, the geometries, and the energies and the shapes of the already present molecules. So again, we should have another molecule like this, which need to be explained. This is a molecule. Okay, now what experiments suggests? Experiments say that all these bonds between these bonds, they have the same energies and the same lengths. Same energies I should not use this one, and same bond lengths. Okay, this one. Okay, and there is one thing else. I'm not mentioning this one because in next lectures we will just look at why CC bond is a bit smaller or larger. But right now I would just say that length of these 4 bonds is similar. Okay, same. One of this bond has this bond is a little bit more in length than those bonds. Okay, it will be clear in this video a little bit. Okay, and the angles between those things are 120 degrees, about 120 degrees, 120 degrees and 120 degrees. Okay, so again 120 degrees. What about our old friend methane? It has 109.5 degrees angles between each CH bonds, and each CH bond there was Sp3 hybridized. Here this thing we don't still know. Suppose it's a molecule, how it will be explained. So hybridization explains it by assigning it a Sp2 or Sp2 hybridization to the carbon atom. So first, these are molecules, these are the orbitals which need to be overlapping. Okay, the molecule is already there. Experimental values of the lengths of the bond, energies of the bonds, and the angles of the bonds are already there, but hybridization is just going to explain that. Okay, suppose px or py or pz, forget about this, one of them is left out. This is p. Now you have a situation. What happens? One s orbital and two of the p orbitals combined together. Okay. So previously we just assigned some energy to it. Let's assign it again to it. We just assigned, it's just a random energies just to make you understand. Suppose a p orbital has an energy of 12 and s orbital, and the 2p orbital has energy of 10. And these are two p orbitals, 1 and 2, 1 plus 1, 2, and one of the 2s orbital which has energy of 10. They all mix together. So what happens? Three things mix together, and what will be their energies? So p plus s, 2p and 2s. Okay. Suppose 12 and 10. 12, or now what will be the average energy of these hybrid orbitals? Okay. These three mix together and they form some blend or a mixture type of orbital which is called Sp2 hybrid orbitals. Just we are now saying, because we want to compare its energy with the CH4 Sp3 bonding energies. Okay, so what will be its energies? 12 34 divided by 3, 34 divided by 3, it comes out to be about 111.3 roundabout. Okay, it is about 11.3, about 11.3. So what was the energies of the CH-Sp3 bonds? In previous video we saw that it was 11.5. Now what here will be the it was suppose what was the energy of the Sp3 orbital or random energy? It was 11.5. Now what is the energy of these orbitals? Because s orbital has now a greater proportion, or p orbitals are not 3, they are 2. Okay, so its energy, the sp2 orbital is lower in energy than sp3 orbitals. So one thing we can see, and it should be clear to us. Okay, so how to say that? Suppose we write it in an energy way. This is sp3 hybridized orbital and this is sp2 hybridized orbital. It has energy of 11.5. These are just random values, but to make you understand. And it is 11.3. What we are comparing it to, what is 11.5 and 11.3, where they come out? We just assigned values to 12 to this one and 10 to this one. Okay, so we are comparing it with those things. So sp3 is very much near in energy to the p, and it is again near to the p than s. Okay, so but it is lower, the sp2 is lower in energy than sp3. This is one thing. Okay, so what happens in the hybridization? Three things combined together and it will produce 3 orbitals. Okay, now again let's go for the shapes. The shape of the sp3 hybridized orbital was like this. Okay, now let's exaggerate this thing. This is one lobe and this is other lobe. sp2 hybridized orbital has this lobe bigger and this lobe a little bit more smaller, because the p character here is less. Okay, the p character here is more, so it has less energy and it has this lobe smaller and this lobe out. So what about the lobe out and the lobe in? Let me tell you. If you want to combine two things together, okay, if this is these are two magnets, suppose, or something else, iron or magnet, they attract each other, and you have this area available, it will attract each other, and it will require a force to separate them. But if this has this much area, okay, so now, and this is a big magnet, now it can stick very hardly with it, and it will require more force to separate them. So these orbitals are a little bit, I should exaggerate those. They're a little bit more bigger, not bigger in length, okay. I will tell you that the length of these things are smaller. Suppose sp orbital, it can just form a bond like this, and this can form a bond like this, okay. So these are more deep, okay, or they can strongly overlap. So you should remember that sp2 or orbitals can overlap strongly than the sp3 orbitals. The thing is because it can provide strong surface, a little bit more surface area for attachment, or it is lower in energy than the sp3. Okay, this thing is a little bit clear. Now, how what will be the fate of this orbital? Okay, so as you saw that you will have these orbitals. Suppose these are the energies of the, you have 3 multiply how many, 1 2 3 3 multiplied by sp2 orbitals, okay. Hybridized orbital, 3 hybridized orbitals are there. It can form a bond, and this is suppose its energy, and its energy what we calculated roughly, not roughly but with our own estimation, was 11.3. But it remember, one of the p orbital is remaining in the molecule, and this p has energy of 12. A high energy orbital is here also. Now let's come to the geometry, or first the arrangement, that how these 3 will be arranged, and how the fourth, what to do with the p orbital, okay. So shape, we saw that it has a little bit more bigger lobe, and the other lobe is a little bit smaller, okay. How they are arranged? Actually the 3 p orbitals, sorry, the sp3 orbitals, they are arranged like this. This is carbon in the middle, and these are the 3p orbital. They are arranged like this, okay. So the angle between these things is 120 degrees. And what about the what about the p orbital? Now you will see. First we saw that its shape is, its smaller lobe is even become more smaller, and bigger lobe is a little bit bigger. So I have roughly made this thing. So these orbitals look like this. So these are just roughly 120 angles, okay, just like a fan, or okay, the blades of a fan. Suppose these are sort of 120 angle to each other, they are like this, okay. So now we saw that the sp2 orbital, how they are arranged? They are arranged like a fan, 3 blades of a fan, or 120 angle, 1 2 3. This is our carbon. In the center this is carbon, and these are just the orbitals, okay. Each orbital has 1 electron in it, okay, and this each electron is capable to form a bond, okay. So now, but as you know that there is another thing. What about the p orbital, unhybridized, the high energy one? How to accommodate it? Vesper theory said that when 3 things are there, okay, they will be arranged in such a way that the angle between them will be 120 degrees, okay. And this thing is trigonal planar. Trigonal planar means that it has 3 legs or blades, and it's planar. Planar means that it can be on same plane, flat. You can write it just like a flat thing, okay. But what about the p orbital? So the p orbital should be perpendicular to those 3 orbitals. How? As you know that the p orbital has 2 lobes, big and small. Sorry, both equal. This is p orbital, and this is left with us. What to do with this thing? So again, let assume that this pencil is the p orbital. This is our sp3 orbitals, okay, sp2 one orbital, sp2 other, and the sp2 other. How it will be now, look at this. This is half and this is the other lobe. P orbital will be perpendicular to them, okay. We are now going to show, I am going to show you this molecule. This orbital which has one electron, this has one electron, this has one electron, and the p has one electron again. This one will form a covalent bond with the hydrogen atom. This one will form a covalent bond with the hydrogen atom, okay. And this will also form a covalent bond, but with what, okay. So as you saw that this thing has 2 carbon atoms, okay. We discussed this one, okay. It is sp2 hybridized carbon. This carbon is sp2 hybridized. Let me write it like in some easy way. This is one, this is other, this is the other, and okay, suppose we are discussing this one, this carbon. So this one is attached with the hydrogen, this one is attached with the hydrogen, and we don't know. This is the sp2 orbital, this is the sp2 orbital, this is the sp2 orbital. 2 are attached with the hydrogen, and the third we don't know. Now, as you saw, this is the p orbital, okay. This is the p orbital. So this is the arrangement, okay. And the long one, here it is. This is the thing which we don't know, this orbital. This is our p, half up, half down. These are the 2 which are attached with the hydrogen. One hydrogen is attached with this, the other hydrogen is attached with this. So how to write this on board or 2-dimensional surface? So this thing, this hydrogen is toward you, this bond. So the way to write it is like this, bold. And the other one, dotted line or hash. This is away from you, this is toward you, and this is in the plane of the board, on the board plane. Now what happens? This carbon again, this is carbon another carbon is there, and it is also sp2 hybridized or sp2 hybridized. So if it is again sp2 hybridized, so what will happen? Which pen? This pen, okay. Suppose another carbon, this one, it is sp2 hybridized. So it again is like this thing, okay. It is attached to 2 hydrogens, we know, and it has again a p orbital, okay. But now these 2 form a bond with each other. And as you know that this has 1 electron and this has 1 electron, so they loosely overlap with each other, okay. They overlap with each other a little bit loosely. So this is the shape, and the angle between those 2 is 102, 120 degree. This is 120 degree. This is a stronger bond, CH_sp² bond, and the other one is a little bit weak bond. So again, I should use some homemade models of mine. Okay, this one is 1 carbon. This is the other carbon. So this is 1 carbon. This is the other carbon. 1 hydrogen white. This other hydrogen, other hydrogen, other hydrogen. So how the p orbitals in the in this molecule overlap with each other? Look at this. Oh God, the one p orbital is bigger, the other is smaller, so I have to use similar size things. Okay, these are the 2 p orbitals. Now this is the ethene molecule, okay, hydrogen, sp² bond with the hydrogen. The middle one is carbon, okay. The p orbital is half above and half below the nucleus. It's not half, but it is in reality it is half, but this thing is a little bit tight, so I can't do it. Hydrogen, hydrogen, okay, with hydrogen, with hydrogen. The pp overlap above and below. Okay, so that's how the ethene molecule look like. Okay, so again let me write something on board. This is our molecule. So now you know, let me tell you one thing else, that how this molecule is placed on a board, because the board is two-dimensional. It's like this. This is hydrogen. Suppose this is hydrogen 1, hydrogen 2. This is hydrogen 3 and random number 4. Okay. Hydrogen 1, hydrogen 2. It's not like this, okay? It's like this. Hydrogen 3, hydrogen 4, and these are the p orbitals. These are the p orbitals, and they overlap in the downside also, okay? Now it's good. So it has one electron, these overlap with each other, these also overlap with each other.